GaN's more reliable than silicon. So that's the starting point. And it comes back to the chemical bond between gallium and nitrogen, which is stronger, makes it less sensitive to temperature effects that affect silicon. GaN fundamentally is based on a crystal that is much, much more strongly bound than silicon. And it's called a wide band gap semiconductor as a result. Now, because it's a wide band gap, as you go up in temperature, the effective temperature is much less because it does not impact thermal electrical characteristics as much, and it doesn't affect reliability as much. So, for example, if you put unlimited current through our devices, it can withstand a much higher temperature before it blows up. And that is something that is a robust factor. So we can show that, first of all, silicon stops being a semiconductor at 300 degrees C. GaN devices, you can operate happily at 300 degrees C. It's the rest of the circuit that doesn't like it. And as a matter of fact, it won't blow up until 600-700 degrees C. What we did was we took every single stressor that you can think of, and we figured out what is the wear out mechanism for that stressor. For example, voltage. What makes a GaN device wear out because of voltage gate to source, voltage drain to source, voltage applied very quickly? What are those wear out mechanisms? And the way you do that is you take devices until they fail. And usually that means going to fairly extreme conditions. And then by understanding the mechanism that caused them to fail, you can then interpolate back into rational conditions. And usually the answer is longer than the age of the universe. And we've demonstrated that. And I can also say that in our lifetimes, GaN will not wear out except for thermomechanical effects, which are the same ones you have in any semiconductor component. So it's the joint between your gallium nitride or your silicon device and your printed circuit board or your ceramic substrate. That's what wears out with GaN. Not true in silicon, but in GaN, that's the one thing. In a MOSFET, you have something called a Spirito effect. And the Spirito effect has to do with the fact that in a MOSFET, the threshold voltage dramatically reduces with temperature. Now, as the threshold goes down, if you have the same amount of voltage in your gate, it will actually cause the device to draw more current. Now, think about that locally in a device. If one little tiny spot of that device gets a little bit imbalanced, it will start drawing more current, which will make the threshold go down more, which draws more current, which makes it go down more, which makes it blow up. That's the Spirito effect. It does not exist in GaN devices. The threshold voltage has a very low temperature coefficient of any kind. So the safe operating area is a true, safe operating area where you have your voltage on one end, you have your maximum current at the top, limited by on resistance. There tends to be a curve where you just can't address it because of on resistance. And then you have a constant power, 45-degree angle on these charts. In a Spirito effect, that actually gets bent and it goes down like that. In GaN, it's a 45-degree angle. Just keep it under the temperature limits. It's when you get something bad, like a short circuit, that GaN will survive more than silicon will. It's when you put it up in space that GaN will survive much more than silicon. Because GaN can be made to be radiation, not just resistant, but just impervious to radiation. But it's also 100 times higher performance than radiation-hardened silicon, which typically is not nearly as high performance as commercial silicon. So you get 100x performance advantage plus no shielding required. And it's enabled new topologies to be used in space electronics, which further shrink things and increase the efficiency. So we like to start our designers on what's the thermomechanical environment that this device will see, what's the mission profile, and let's work from there, because nothing else is going to phase GaN. Understanding your thermomechanical environment. So, typically it has to do with what are your temperature excursions, how frequent are they, and how fast are they. So thermal design, like how you do heat sinking, how you lay out your board, can all affect those things. And if you understand it, you can design around it and mitigate it. we give all sorts of ways to mitigate thermal designs in our, again, the textbook that we wrote. And there's some simple things about layout. There's some more complicated things like underfill or pinning the corners of a device to prevent so much differential thermal expansion. Also, the selection of the device can be very important, whether you a package device or a chip scale device. Also, the size of the device matters. If you want a very big device, it will have less thermal mechanical tolerance than a small device. So sometimes in a very extreme environment, get two devices in parallel rather than a big device.